Unit 4, Lesson 16 also has no new lesson notes, so I'm going to go right into the examples here. So here are the examples for this lesson. The population in millions of country C is given by the equation f of t equals 16 times e to the 0.02t. The population of country D is given by g of t equals 17.5 times e to the power of 0.025t. In both equations, t is the number of years since 1980. Will there be a time when the two populations are equal? Explain or show your reasoning. So the easiest way to figure out whether this will happen is to graph both of these functions on Desmos with the understanding that instead of typing in t, I'm going to type in x. So it will graph. So let's go to Desmos. Okay. So it is, the first function is 16 times e to the power of 0.02t. So this will be 0.02x. So 16 times e to the power of 0.02x. And then the other one is going to be 17.5 times e to the power of 0.025t, or in this case, x. Okay, now it looks like there's no graph on my screen here, but of course I know I have to zoom out. Okay. And if we look, there is an intersection point here. The problem is that that intersection point occurred before our initial value. So in this case, it occurred before 1980. The initial values were in 1980. If I just look in positive numbers, you can see, if I zoom out even more, the graphs aren't going to come close to intersecting again. So there is a time that they are the same. Okay. The problem is that point in time occurs before 1980. So negative 17.9 means it happens almost 18 years prior to 1980. Okay. So will there be a time when the two populations are equal? So the answer is yes. Okay. Yes, because the two graphs intersect. However, that time occurs before 1980, since the t value, or in the case of the graph, the x value, since the t value of the intersection points is negative. Okay. So there's your answer to number 1. Number 2, at some point in time, the population of country C reached 30 million. Okay. When does this happen? Explain or show your reasoning. So country C was this function right here. and we want to know how long it takes to reach 30 million. So what I'm going to do is I'm going to take this function, 16 times e to the power of 0.02 times t, and I'm going to set it equal to 30, okay, with the understanding that 30 really means 30 million, okay? So that's how I'm going to figure that out. What I'm going to do is I'm first going to isolate that exponential term. So I'm going to divide both sides by 16, okay? So 30 divided by 16, okay, is 1.875. So e to the power of 0.02 times t equals 1.875. All right, I can now convert this to log form. So this will be log base e of 1.875 equals 0.02t. Okay, switching around the order, that's 0.02t equals log base e of 1.875. All right, and then I will simply finish that off by dividing both sides by 0.02. So t is going to be equal to log base e of 1.875 over 0.02. Or we could write it as t equals ln of 1.875. So natural log of 1.875 divided by 0.02. So either one of these would be considered correct. If I were to actually go ahead and find, to give us an idea of how much that is, if we go on Desmos, okay, again, if I go to functions, miscellaneous, notice this is the log function we've been using. So I could do log base e of 1.875 divided by 0.02. So it's a little more, it's almost 31 and a half years after 1980, to give you an idea. Okay. So it happens almost 31 and a half years after 1980. Okay. And that is it for the examples for lesson 16. And that is it for lesson 16.